There's one rule in physics that feels less like a scientific equation and more like a grim fact of life.
Oh, I think I know where you're going with this.
It's the rule that says you can never, ever unscramble an egg. It's why your coffee gets cold, why my desk is always a mess, and why, allegedly, the whole universe is just marching towards this lukewarm gray death.
You are talking about the second law of thermodynamics. Such a cheerful topic.
The second law, exactly. Entropy always increases. Things fall apart. It's like the ephemeral motto of the cosmos. But, and this is why we're here, we've been digging into a paper by Jerry Z. Liu titled The Easiest Way to Grasp Entropy. And it says maybe we've got it all wrong.
It's a pretty bold claim. I mean, we are about to dive into a paper that challenges what is arguably the most sacred cow in physics.
Right.
The source argues that the second law isn't this universal, unbreakable rule. In fact, Liu says that for huge parts of the universe, we're talking stars, black holes, maybe even the planet under our feet,
Yeah.
entropy actually decreases.
Okay, I have to stop you right there because I thought this was, settled science, like gravity. You don't get to just opt out of it. If entropy doesn't always increase, does that mean I can unscramble an egg?
Well, no, not exactly. The egg stays scrambled.
Yeah.
But the argument here is that the always increases rule is really specific. It's for systems that push apart, like gas in a steam engine.
Okay.
But when you look at systems where things pull together, where gravity is the boss, the rules they flip.
So we've basically taken the traffic laws for a quiet little suburb and tried to apply them to a Formula One racetrack. Is that the idea?
That is a fantastic way to put it, yes. And if this source is right, it changes the entire story of the universe.
How so?
Instead of this slow march toward heat death, the universe might actually be a machine that's built for restoration.
I like the sound of that a lot better. But, okay, we have to earn that optimism. We really need to unpack this. We have to strip away the jargon, figure out why the rule works for an ice cube but fails for a black hole, and we definitely have to talk about the feud between the two definitions of entropy.
Ah, yes, the showdown.
Because apparently physicists have been using two completely different dictionaries.
It's classical thermodynamics in one corner and statistical mechanics in the other. They're usually treated as the same thing, but this paper suggests they're describing fundamentally different territories.
All right, let's start at ground zero then. What is entropy? Because usually people just wave their hands and say disorder. A messy room has high entropy, a clean one has low entropy. Is it really that simple?
Not really. And honestly, that whole disorder analogy, I think it causes more confusion than it solves. Liu wants us to look at the physical reality. In classical thermodynamics, there's a very intuitive equation. It's equation 1 in the text.
Okay.
It defines a change in entropy very simply. It's the amount of heat you transfer divided by the temperature. That's it.
So, d chair equals dq3 tau. Heat divided by temperature.
That's the definition.
Okay, so mathematically, if I add heat to something, the top number goes up, so entropy goes up. Seems straightforward enough.
Yes. But here's the nuance, and this is where people get tripped up. The paper points out that entropy rises on a logarithmic scale compared to temperature.
Okay, logarithmic is a word I haven't really used since high school math. I know it means a curve, but what does that actually mean in the real world? Why does the shape of that curve matter?
It matters because it tells you about sensitivity. Think of it like this. You're in a dead silent library.
Okay.
If someone whispers, hello, just a tiny bit of sound energy, everyone hears it. It's a huge disturbance.
Right, high impact. The librarian gives the look.
Exactly. Now imagine you're at a heavy metal concert. Speakers are blasting. That same person whispers, hello, with the exact same energy. Does it change anything?
No, you wouldn't even notice. It's a drop in the ocean.
That is logarithmic sensitivity. And Liu argues entropy works the same way. Temperature is the background noise. If you have a very cold system, the quiet library, and you add a little bit of heat, entropy jumps up a lot. But if the system is already scorching hot, the rock concert, that same amount of heat barely moves the needle.
That actually makes perfect sense. So entropy isn't just how much heat is there, it's how much does this new heat matter right now?
Precisely. It's all about the impact of that energy distribution relative to the current state.
Okay, so if it's just heat over temperature, why do we always say it always increases? Why can't I just cool something down and lower its entropy?
You can. You put a hot pie on the windowsill, it cools down, its entropy drops.
Right, but then my physics teacher would pop up and say, but the air outside got hotter, so the total entropy went up.
And your physics teacher is right in that specific case. And this brings us to why we think it always goes up. The paper walks us through the math. Imagine two objects, one hot and one cold, tall cold.
Okay, and heat flows from the hot one to the cold one.
Spontaneously, yes. So the hot object loses some heat, its entropy goes down. Let's say it loses 5 units of entropy,
Okay, so it's at -5.
but that heat goes into the cold object. And remember the library.
The cold object is the library. It's more sensitive, so that heat makes a bigger impact.
Correct, because you're dividing that heat by a smaller number, the lower temperature. The entropy gain in the cold object is bigger than the loss from the hot one. So maybe the cold side gains, say, 10 units.
So -5 on one side, +10 on the other. The net result is +5.
The total entropy increases. This is the second law. The source calls it evolution toward uniformity. Energy spreads out until everything's the same.
This makes perfect sense. This is my ice melting. This is my coffee getting cold.
And this is where the source makes its critical point. This whole mechanism, this drive toward uniformity, it works because it's dominated by repulsive interactions.
Repulsive, you mean the molecules are literally pushing each other away?
Exactly. Think of a gas. All these molecules zipping around, bouncing off each other.
Yeah.
They want to claim as much personal space as they can get. They're the spreaders.
The spreaders. I like that.
And when you have a system of spreaders,
Yeah.
gases, liquids, steam engines, the second law is king. They want to mix. They want to be uniform.
So we've basically spent a century studying steam engines and just assumed the entire universe is one giant steam engine.
That's a pretty good summary, yes.
But
Yeah.
the universe isn't just gas, there's something else.
Enter the collector. Gravity.
Okay, let's talk about gravity.
Yeah.
Because when I drop a glass, gravity smashes it into a million pieces. That looks like disorder to me. That looks like entropy is going way up. How can gravity possibly be an ordering force?
That's a great question. But you have to zoom out. Don't look at the broken glass. Look at our atmosphere.
The atmosphere.
If the atmosphere followed the second law like a gas in a box, what would it do?
It would spread out
Yeah.
evenly.
It would try to be perfectly uniform. The air at the top of Mount Everest would be just as thick as the air at sea level. Everything would be a boring, equal mist.
But it's not. It's thick down here and thin up there.
Exactly. It's stratified, it's layered. Gravity is pulling the air down, fighting that tendency to spread out. The system is actually ordered by gravity. It's maintaining a structure.
So gravity is in a tug of war with the second law, saying, no, you don't get to spread out. You stay right here.
In a way, yes. Gravity creates gradients, differences. The second law wants to erase them.
Okay, I see that with the atmosphere, but what about bigger? The paper talks about the formation of the universe.
The cosmic contradiction.
Yeah.
Think about the early universe. It started as these vast, giant clouds of gas, really low density, very spread out.
It's a maximum uniformity, basically.
Right. If the universe only cared about maximizing entropy, those clouds should just stayed clouds or spread out even more.
But they collapsed. They formed stars.
Gravity pulled them in. The collector took over. The gas clumped together into stars, planets, black holes. That is aggregation. It's concentration.
Hmm.
The universe went from a spread out mist to these intense points of concentrated energy.
That sounds like the exact opposite of energy spreading out.
It is. The source argues that this is a decrease in entropy. The universe is naturally building structures, not just tearing them down. A star is a highly ordered, concentrated thing compared to a random cloud of gas.
Wow. That's a huge shift in perspective. We're always told the universe is winding down, but this sounds more like it's winding up.
Locally, absolutely. And the paper gives an even more extreme example. Black holes.
Ah, the ultimate vacuum cleaners.
This is where the math really gets turned on its head. The paper describes the energy flow near a black hole. Now, deep space is cold. Very, very cold. Close to absolute zero.
And a black hole.
The black hole has immense energy. Gravity is pulling everything in.
So you have radiation heat moving from the cold of space into the high-energy black hole.
Precisely. Remember our rule. Heat flows from hot to cold. Here, gravity forces energy to flow from low-temperature space to the high-temperature black hole.
That's the complete reverse of the ice cube example.
Exactly. The hot thing, the black hole, is sucking in energy from the cold thing. It's feeding.
And if you run the numbers on that,
It's what the paper calls an anti-gradient flow. The total entropy decreases. The system is becoming more concentrated.
so black holes are basically entropy-reducing machines.
According to this source, yes, they are points of massive concentration. And it's not just in space. The author brings it down to a kitchen experiment with supercooled water.
Okay, I've seen videos of this. Water that's below freezing but still liquid, you tap it, and it instantly turns to ice.
That's the one. Now think about the heat. When that water suddenly freezes, it has to release heat, right?
Mm-hmm.
Ice is a lower energy state.
Right, it kicks that extra energy out.
Yes. But here's the wild part. The paper notes that in this setup, the heat can flow from the freezing water, which is cold, to the container, which can actually be warmer than the ice being formed.
Wait, hold on. Say that again? Heat is leaving the cold water and going into a warmer container.
Yes.
But that breaks the rule. Hot to cold, you're saying it's going cold to warm.
In this specific phase transition, yes, because the attractive forces, the molecular bonds forming the ice crystal, are so powerful they force the energy out. They prioritize building the structure over the normal thermal gradient.
So the water is so desperate to get organized into ice that it literally pushes heat upstream.
That's a great way to put it. It's an anti-gradient energy flow. The water is ordering itself, lowering its entropy, and the energy transfer actually supports that organization.
Yeah.
It proves that when attractive forces are in charge, the simple hot to cold rule doesn't always apply.
Okay, so we have stars forming, black holes concentrating energy, even water freezing. All these examples of nature choosing order. Which really begs the question, why have we been so convinced that chaos always wins?
And that leads us to the big showdown in the paper, the duel of definitions.
This part was dense. The source claims that scientists have been using two different definitions for the word entropy and just pretending they're the same.
It's the clash between the classical view heat over temperature and the statistical view.
Statistical entropy, that's Boltzmann, right? The equation on his tombstone.
Goes Elian. Entropy equals a constant times the logarithm of the number of possible microstates.
Microstates, the number of ways you can arrange things.
Exactly. A messy room has a million ways for your socks to be on the floor. High entropy. If they're all folded in the drawer, there's only one way. Low entropy. It treats entropy as a probability game.
But the source has a big problem with this.
A huge problem. The source argues that counting microstates is mathematically ambiguous in continuous real-world space.
How so?
Okay, picture a line that's 1 meter long. How many points are on that line?
An infinite number.
Now imagine a line that's 10 meters long. How many points?
Still infinite.
Right. You can't say the 10-meter line has more points. They're both uncountably infinite.
So saying a gas in a big box has more states than a gas in a small box
Is mathematically shaky, according to Liu. You have to draw an arbitrary grid on reality to even start counting. The source argues that statistical mechanics describes the probabilistic distribution of things, like checkers on a board, while classical thermodynamics describes energy distribution. They aren't the same.
And the paper points to where they really crash. Absolute zero, the 0 Kelvin divergence.
This is the smoking gun of the argument.
Lay it out for me.
In the statistical view, at absolute zero, everything stops. There's only one possible state, the ground state.
So the log of 1 is 0. Entropy is 0. Simple.
Correct. But now look at our original classical equation, 0 dolly equals dqdt.
Heat divided by temperature.
As the temperature, T, gets closer and closer to 0.
Oh, you're dividing by 0.
And when you divide by a tiny, tiny number, you get a massive number. The equation implies that as you approach absolute zero, entropy just dives off toward negative infinity.
Whoa. So one definition says you have reached 0. The other one says you have reached negative infinity.
Try.
That is not a small rounding error. That's a completely different reality.
It's irreconcilable. And the paper points out that even at 1 Kelvin, statistical entropy has to be positive, but the classical equation could still be 0 or negative. The two models just don't match up.
So if they don't match, is one of them wrong?
The source implies they're for different things. Statistical mechanics is great for probability, but classical thermodynamics is about energy. And the second law, this idea of heat death, is a classical concept.
But we've been applying it to the whole universe.
Exactly, and that's the main takeaway. The second law is a brilliant rule for specific repulsive systems like gases. It's not a universal command for the entire cosmos.
So if the universe isn't just decaying into a messy soup, what is it doing? What's the alternative to heat death?
The paper introduces something called the restoration principle. Think about a pendulum. It swings up, converts kinetic energy to potential. It swings down, converting it back. It doesn't just run down, it cycles.
Right.
The restoration principle suggests the universe is more like that. It's not a one-way street to destruction. It's a continuous transformation of energy. Kinetic becomes potential, potential becomes radiative, and back again.
So instead of a flat line, it's a heartbeat.
That's a beautiful way to put it. It can be reversible, it can be periodic. The universe isn't dying, it's breathing.
That feels a lot better.
And it connects right back to Einstein. UMC 22. Matter is just concentrated energy.
We're frozen light.
Exactly. So when the universe forms a star or a planet or you, it's taking spread out energy and concentrating it into complex matter.
So gravity is the builder?
Gravity is the builder.
Yeah.
And the source asks us to really think about it. Is the universe actually a machine for building complexity, driven by gravity, rather than just a box of gas spreading out?
That's a huge thought. We look at the stars and think they're burning out, but maybe the process of making them in the first place is the universe's main job.
It really challenges that sort of nihilistic view of thermodynamics. As long as there's gravity, there's a drive towards structure,
Mm.
towards something more.
So, next time you break an egg, don't sweat the heat death of the universe. That's just a little repulsive system doing its thing. But look up at the sun, the moon that's gravity holding it all together, fighting the chaos.
Exactly. The universe has two hands. One scatters, but the other one gathers.
This has been a fascinating look at the easiest way to grasp entropy. It's a great reminder that even the oldest rules in the book are worth re-examining.
Always question the assumptions.
Thanks for listening to this deep dive. We'll catch you on the next one. Stay curious.